Hi everyone! Welcome back to another live stream event with the Planetarium. My name is Jessica. I am the director of the Planetarium, and with me today I have one of my students, Eli. I'll let him introduce himself.
Hello, I'm Eli. I am a physics student at UMD.
And so Eli, our mysterious voice in the sky, as he is normally in our streams, is going to be watching the comments for any questions you guys might have during the show today. And so we're going to be talking about exoplanets or extrasolar planets. These are planets found around other stars. And there's a lot of cool things that we have found with it. But first, we're going to look at kind of how we find these things, and then take a look at some of the interesting and weird planets that we have found. And so, again, if you have any questions throughout the show, write them down in the comments. Eli will be watching for those. Just a reminder that there is a little bit of a delay between when we see a question and you're going to hear an answer. So give it a little bit, but if we don't get to it right away, we will take time at the end to answer any questions that have come up that we haven't gotten to. So let me switch over. Oops, did not mean to hit share. There we go. And so, yeah, we're going to be looking at the wild world of exoplanets. And so there are many different ways that we can find planets around other stars. But we're going to look at the two main ways. The first way has a kind of fancy name called radial velocity method. And I think it's best to think of it as kind of a gravitational tug. That we're looking for. And so before we can get into exactly what this is, there's a couple of things that we have to understand that are kind of some common misconceptions or things that people don't really know. And so we know that the Earth has gravity, right? We know that Earth's gravity is what's holding us onto the planet. We also know that Earth's gravity is pulling on the moon and holding the moon in orbit around the Earth. But what you may not realize is the moon has its own gravity and also tugs on the Earth. And the same thing with the Earth around the sun. We know that the sun's gravity is what holds Earth in orbit around the sun. But the Earth is also tugging on the sun as well. And so both of these things are kind of pulling on each other. Now, the other thing we have to understand is when we say something like the Earth orbits the sun, that's technically incorrect. What's actually happening are both of the sun and the Earth are orbiting around each other around a point we call the center of mass. And so this is really easy to kind of imagine with if we have like two things that are the same size, so like two stars that are the same size. This center of mass is like a balance point. And if you have two things that are the same size, that balance point is going to be right in between them, right in the middle, like we can see on the left here. And so these two stars would actually orbit around that point right in between them. Now, if we have a system instead that has one star, for example, is a little bit more massive, then that balance point is going to sit a little bit closer to the bigger star. But we can see that both are still orbiting around that common center of mass. Now, if we go even more extreme, with one object being much bigger than the other, then what can happen is that common center of mass is actually inside of the bigger object. And so this is what happens with like the moon orbiting the Earth or the Earth orbiting the sun. That common center of mass is actually inside of the sun, for example, with the Earth and the sun. And so because of that, the Earth does orbit around the sun is also wobbling a little bit, as it also orbits around that common center of mass. And so this is what we can look for when we try to find planets around other stars. Because finding a planet itself is extremely difficult. They're very, very small, they're not that bright, and so we can't rely on being able to directly see a planet. Instead, we have to look for clues that a planet might be there, like a wobble of a star. And so this wobble can tell us that there is a planet there orbiting around. And based off of how much the star wobbles, we can find out things like how massive the planet is. Based off of the amount of time it takes for the star to make one wobble around, we can figure out how far away from the star the planet is. And so there's a lot of stuff that we can do with this. Now, I'm not going to get into too terribly much detail about how exactly we do this, because this is an entirely separate show, being able to talk about how from the light of the star we can kind of discern that it's wobbling. And we actually are going to be doing a show about this. We're in the works of doing at least one show, or maybe a series of shows, tentatively called Learning from Light, since 90% of astronomy is learning from the light that we receive. And so we're going to get into that at a later time. But this is one way that we can search for planets, is we, from the light coming from the star, we look for evidence that it's kind of wobbling, that it's orbiting around something, and that can tell us that there is a planet orbiting around the star and give us information on the planet. Now, another way that we can do this is a method that we have actually talked about on our shows before, and this is what we call the transit method. And so this is relying on the fact that some planet and star systems are going to be aligned just right so that when we look at them, we can occasionally see the planet cross in between our view, us and the star. And so as it's moving across our view and across the star, it blocks some of the star's light. And so when we see the star, we see that the brightness of the star dims. It drops a little bit. Now, one of the great things about this is based off of how much the star's light dims, we can actually figure out the size, the radius of the planet, because a bigger planet is going to block more light and cause a bigger dip in the star's brightness. Now, there are some downfalls to this. Obviously, this is only going to work for systems where the planets do lie in between our view of in between us and the star we're looking at. So you can imagine that there are a lot of systems that we can't see and can't find just because they're not in the right orientation for us to see a transit. The other problem with this is planets are way smaller than stars. Like the example you're seeing here is pretty exaggerated of the size between the star and the planet. So if, for example, we want to find an Earth-sized planet, we're actually looking for a drop in the star's brightness of about 0.01%. That's a tiny little bit. And so we have to have very accurate instruments to be able to measure stars' brightness well enough and accurate enough that we can tell when there is an actual dip. The other kind of worry, or I guess caveat to this, is there are a lot of reasons a star's brightness could change. There are things like sunspots. Stars' brightness in general can just kind of fluctuate and change. And so seeing a single instance of the star dimming does not automatically tell us that there's a planet there. Instead, what we want to look for is for this dimming to happen at least 3 times in a regular period, which indicates that something is going around and blocking the star's light each time it orbits around, rather than just being a random change in the star's brightness. Okay, so this transit method is primarily how we have found planets around other stars. And a good chunk of that work was done by the Kepler Space Telescope. So this launched in, oops, my slides are incorrect. It's March of 2009, not May, and worked for about 9 years before it was retired in 2018. The Kepler Space Telescope, when it was launched, was actually the largest telescope put into space at the time it was launched. Its mirror is about 55 inches in diameter. And its initial goal was to monitor the brightness of 150,000 stars every 30 minutes. So for 150,000 stars, it took pictures of them every 30 minutes so that we could have lots of information and lots of detail to try and find this kind of regular dimming that could indicate the presence of a planet. Now, over its just over 9 years that it was working, there have been 2,662 confirmed planets found by the Kepler Space Telescope. Many of these are Earth-sized planets, which is very exciting. And we have another about 3,000 more candidates. And what we mean by this is we see like a single dip, but scientists are still working to comb through the data or get more data on the star to see if it's a regular occurrence and not just a random change. Now, just before Kepler was retired in October of 2018, a new satellite named TESS was launched in April of 2018, and it's kind of a continuation of Kepler, or a kind of successor to Kepler. But TESS was designed to do even more. It has 4 cameras, which allow it to take 4 different images of different parts of the sky at the same time, which allows it to cover a much broader area of the sky than Kepler was. And so the goal of TESS was to have an almost full sky survey of stars monitoring their brightness. And so it's covering about 85% of the sky and taking pictures, I believe it's like every 10 minutes. So again, it's an extraordinary amount of information that it's gathering for us. Now, in the couple of years that it's been active, it has found 45 confirmed planets and about 2,000 more candidates. Again, these are ones that we think could be, but we're waiting on more information to confirm whether it is a planet. And so there is a lot out there. With our explorations of planets around other stars, we have found that they are very common. It's estimated that at least half of the stars in our galaxy have a planet orbiting around it. And that's 100 billion stars, so that's at least 50 billion planets. That's a lot. Now, with these searches, we have found a very wide range of things. We have found some that could be similar to planets we see here in our solar system. We've also found some that are really bizarre. And so for the rest of this, I want to take you through some of the interesting and weird planets that we have found. And so we're going to start with a planet that has the totally awesome name of Kepler 186f. So Kepler 186 is the name of the star that this planet was found around, and F indicates that it was the 5th planet found around the star. So the reason we're starting with this one is Kepler 186f is the exoplanet we have found that is closest in size to the planet Earth and lies inside of what we call the habitable zone, which is this kind of green shade we're seeing here. So this habitable zone is, I like to think of it more of the Goldilocks zone. It's the range in distance from a star that the temperatures could be right for there to be liquid water on the surface of the planet. And the reason this is important is we think liquid water is necessary for the development of life. And so this is very exciting to find a planet similar in size to Earth that is similar temperature and therefore could possibly have developed life or develop life in the future. Now, you can see it compared to our solar system. The planet here and the other 4 planets are very close to their star. But this Kepler 186f is still about Earth temperature, even though it's closer to the star, because the star it's going around is a cooler star than our sun. And so you have to be closer to it to be the same temperature as our Earth. Now, another one that is very promising is Proxima Centauri b. So Proxima Centauri is actually the closest star to us, and it turns out that it has a planet. Not only does it have a planet, it has a planet that's roughly the same size as the Earth, a little bit bigger, about 1.5 times the size of the Earth, and it also sits in that Goldilocks zone. And so this is extremely exciting because this is the closest star to us, which has a planet that could possibly sustain life. And so if we ever do figure out how to travel to other stars, this is a great candidate for a good first place to go because it's the closest to us and, could be habitable. We'll see. All right, moving on to some kind of stranger ones. Kepler 16b is the first planet that is confirmed to orbit around a binary star system. And so this is a planet with 2 suns, basically. Now, this planet is about Saturn, and it's about the same size as Saturn, so it's probably a gas giant like Saturn and Jupiter are. But it's really exciting to find that planets can form and be stable around multiple star systems, and you don't have to have just a single star in order to have a system that can have planets around it. All right. So Kepler 10b was the first confirmed terrestrial-like planet outside of our solar system. So terrestrial is a rocky planet like Mercury, Venus, Earth, and Mars. This is more like a super Earth. It's about 4 times the mass of the Earth and about 1.5 times the radius. But what's really interesting and strange about this planet is how close it is to its star. It orbits its star in less than a day. That puts it less than 1/20th the distance between Mercury and the Sun. So it is super, super, super close to its star, which means daytime temperatures on this planet are extreme, reaching almost 3,000 degrees Fahrenheit. And so the daytime side of this planet is hot enough to melt rock and metals. And so the daytime side of this planet is molten, while the nighttime side, temperatures drop to almost negative 400 degrees. And so you have this really weird kind of split here, where we have one side that is super molten hot and the other side that is very, very, very cold. Now, our next planet is kind of an interesting one, Kepler 22b. This is another possible super Earth. It's about 2 times the size of Earth. But based off of what we can figure out about what it might be made of, it suggested that this might be a water world. So a just planet that's covered in an ocean. It also sits in a habitable zone, which is why we think it could have, an ocean, because temperatures could be right for liquid water. So this is another exciting place to possibly search for where life could have developed, because we have a whole ocean of a world, and so there's lots of water there that could maybe prompt the development of life. All right. So KELT 9b is the hottest exoplanet that we have found. It is a super Jupiter, so it's about 3 times the mass of Jupiter and about 2 times the size of Jupiter. But it is so close to its star that temperatures reach about 4,600 Kelvin, which is, to give you a comparison here, about as hot as some low-mass stars get. So this is a planet that's hotter than some small stars. And because it's so hot, it's really puffed up and is actually losing its atmosphere. And that's what you're seeing in this artist's rendition here, is it kind of losing its atmosphere because it's so hot and so puffed up. Now, one of my personal favorites is HD 189-733b. Fantastic name, right? This is roughly the same size as Jupiter, and we think it has this really pretty kind of bluish color, and this blue color comes from silica, like sand. But again, this is another planet that is very close to its star, and so it's very hot. And so instead of being like grains of sand, it's molten sand, so molten glass basically, that is constantly raining down on this planet. But it actually rains sideways because the wind speeds on this planet reach about 5,400 miles per hour. And so you have these insanely high winds blowing molten glass around the planet, and it's just kind of bizarre. And the last two we're going to end with are what I have dubbed the Bejeweled worlds. I just learned about these in my research for this show, and so I unfortunately don't know too much about them. But the one on the left is another super Earth. It's about 9 times the mass of our Earth. And based off of what we think its composition is, it's likely that it is covered in diamonds. And then our planet on the right is a planet larger than Jupiter, and again, based off of compositions of like what gases and stuff we find in the atmosphere, we think it's possible that it is raining rubies and sapphires on this world. So yeah, lots of strange, wondrous things out there. And so hopefully that has given you a little bit of taste of how we find these planets and what we have found. We, of course, one of our biggest goals is to try and find Earth-like planets because we want to know how common they are, which could help us in determining, how common life could be in the universe. But it's also interesting just to see the wide variety of planet types that exist and can form in our universe. It just goes to show how weird and diverse our universe is. So, Eli, do we have any questions?
Nope, nothing right now. All we got was a hello from Shirley De La Torre. Welcome to the stream.
Hi. Well, if you have any questions, try and get them in now. My cat Nova wanted to come say hi. She is a little camera shy, so she doesn't always but she's right here, wanting attention off camera. But yeah, that is the wild world of exoplanets. While we see if there are any questions that are going to come in, let me tell you a little bit about what we're planning on doing next week. So on Wednesday, we're going to have stargazing tonight. So if you're familiar with the programs that we've run in the Planetarium in the past, you'll know that at the beginning of the month, we would run the show called Stargazing Tonight, where we would kind of give you some highlights on interesting things that you could find happening that month. And so that's what we're going to do next week. We're going to do that, tell you some of the cool things you can find in the month of May. But also, Nova, stop. Sorry, my cat is now sitting on my computer mouse and making things crazy. Anyway, We're also going to tell you a little bit about the astronomical significance of May Day, because it turns out there is an astronomical significance to it. So we'll cover all of that on Wednesday. And then next Saturday, we are going to do a show about the aurora, which is one of our very popular shows that we would do at the planetarium. And it's another one that we've been working on updating. And so we're going to do that one for you guys on Saturday and give you kind of a sneak peek at the updated version. And then after that, we have a lot of ideas that we've been playing around with for shows we want to continue doing. As of right now, we still don't know when the planetarium is going to be able to open back up, but we do plan on continuing these live streams until it is safe to do so. Anything coming in, Eli?
No, we just got a great talk. Thank you from Richard John Stevens Jr.
Awesome. Well, glad you enjoyed it. All right. Well, then I guess we'll say goodbye. Enjoy the beautiful day after the past few rainy days. I know I'm excited to maybe go for a little walk, get out of the apartment a little bit. As always, you can find past live streams on our YouTube page. And if you have any suggestions or ideas for shows you'd like to see in the future, let us know. Because we'd love to be able to do, topics that you want to hear about. So yeah, everyone have a great day. Thank you so much for joining us, and we'll see you next time. Bye.